Hey everyone, Nick Dearbird is here teaching you financial modeling. Today we're going to be introducing the second project in the course on probabilistic loan pricing. So this project has a couple of main goals for your learning objectives. One is to have a model where probability is really a first-class citizen, something that we're thinking about very deeply within the base model itself. Probability factors into so many financial models that it's good to hit that early in the course. And then the other main area we're testing here in this project is then to be able to um, extend the base model in different ways. So here we're going to build out an initial model, and we'll have to run that model a bunch of times to understand all the different ways that things could occur. So let's talk about what this project actually is. So the idea here is that you're an analyst within a bank, and the bank is considering doing a loan to a small business. So um, this also gets in the whole debt area and decisions of lenders. Um, so the business needs to buy a machine. They want to borrow money to buy the machine. And then after some amount of time, they're going to repay that loan in full. The interest is paid annually um, at a certain rate based off of the amount that they borrowed. And where the probability factors into this is that the business is not always going to be able to pay back the loan. There is a chance that they're going to default on the loan and not be able to make their payments. So the probability of default here, it starts at an initial probability of default and then it decreases over time because the business becomes more mature year over year. And so it's less likely that they're going to default as each year goes by. But in that final year, when the loan is actually due, the business doesn't just have to pay the interest payment, they have to pay the full amount of the loan, the principal, in addition to the interest payment. So that's a much bigger obligation for that final year. And so the final year has a separate default probability, which is going to be higher than their typical default probability, as over time would say for the interest payments. Um, and so we need to model in what happens whether the borrower defaults or doesn't default. And the borrower can default in any given year that they have to make a payment. So whenever the borrower defaults, then they're going to go into bankruptcy. And we're going to say that the bankruptcy process always takes 2 years. And then after bankruptcy, the lender is going to collect a certain percentage of the original loan amount, the recovery percentage. And so what that means as far as forming the cash flows, in the year that the borrower defaults, then there will be zero cash flow in that year. There will be zero cash flow the next year, and then 2 years after the default, we're going to get the recovery payment as the lender. Recovery times the price of the machine, which is equal to the loan amount. And so that does mean that the amount of cash flows could be greater than the amount of the loan. If they defaulted in the last year, then it's going to be 2 years more than the life of the loan that the final cash flow comes. So this is a fairly realistic kind of model to determine basically what terms should the bank offer on the loan. And so the main question here is, you're the loan analyst trying to come up with what are the appropriate terms for this loan to this bank based on what we know about the bank. Um, and so you're trying to give the loan officer all the information to make these decisions. So you want to be able to say with your model for any given inputs, what's the expected IRR of the loan? And what does that IRR look like for some different interest rates? So here we're going to be looking at 30%, 35%, and 40% interest rates for the loan. And then it goes even further to say that um, there's always a lot of uncertainty in estimating the probability of default. You can never estimate that accurately. So the lending officer wants to see what everything looks like with some different assumptions for the initial probability of default. So base case is 20% per year, but the lending officer also wants you to evaluate 10% and 30% per year. And then the other factor here is how long should the loan be? And so the lending officer also wants to see all the results with 5, 10, and 20 years. And an important thing about how the results should be structured is that your model should show all of these results. It shouldn't require going in and manually changing around numbers to produce these results. Just when I open up the model, I should be able to see the answers for all of these different interest rates, probability of defaults, and loan lives. And then it's also part of the main problem to then visualize your result. There should be graphs and conditional formatting here. So a few notes and assumptions we can add into this to make things easier. So first is that you can assume there's only going to be 20 years of loan life. That's the maximum loan life. If your model can handle more, that's great. But I'm not going to test anything longer than 20 years in your model. But keep in mind that that could be up to 22 years of cash flows if the borrower defaults in that final year. And then as far as the general approach to build out the model, I think it's easiest to go at this with an internal randomness approach. So with the basic structure being that you build out the base model, which just gets you the IRR for one set of inputs, and then you're going to run that base model a bunch of different times with different randomly choosing the default cases. It is possible to do everything in terms of expected value and not actually have a random component in your model, but that does take a lot of fairly complicated math to make that happen. I've only ever seen a couple students do that, and I think it's generally a much more difficult way to go about building this model. And it also doesn't really hit on a lot of the things that I'm trying to test with this model. Going with the internal randomness approach, you're going to get much more comfortable working with a random model and being able to extend an existing model. So that's the approach I would recommend in general. So when you're doing the internal randomness approach, now you're going to be running the model a bunch of times to discover what the true expected IRR is for each set of inputs. Each time it's picking a different default case each time you run the model. So now that it's not a deterministic model, you put the same inputs in and you're going to get different outputs each time. So you've got to keep running it, and then you've got to take the expected value across the iterations to get an actual estimate of the result. And the greater number of iterations you use, the more accurate that answer is going to be, but the longer it's going to take to run your model. So there's a trade-off there, and what I would recommend is as you're building everything out, keep the number of iterations low, just so you can run everything quickly. And then once you think you've got it right, then increase the number of iterations so you can run it a couple of times and check against the provided answers. Um, and then when you actually submit the final, you want to run it with 1,000 iterations before you submit so you can get your final answers in there. And if you've got an Excel model or a combination model, we'll talk more on that in a moment, then it can take a substantial amount of time to run your model with all these iterations. So make sure that you're planning for that time and not just 11:55 p.m. You're done. Now let me try and run this thing with 1,000 iterations. Oh wait, it's taking way too long. So yeah, the next point. This is a big contrast from the last project. Now you have flexibility over the tools that you want to use to solve the problem. I'm trying to really emphasize and help you build a competency in uh, coming to any arbitrary problem and using the tools which are best suited for the job. And so in some cases that might be Excel, in some cases it might be Python, in some cases it might be a combination of the two. So same thing for this project and the remaining projects in the course. You're free to implement it in the way that you like. You can submit a pure Python model, you can submit a pure Excel model, or you can submit a model which uses both tools together. I am putting one restriction on it here, that if you are submitting a combination model, then your final answers should be in the Python side, which I think in general makes a lot more sense anyway, because the most straightforward way to combine them is to build out the base model in Excel and then use Python to run all these different iterations on the model. So then you already have your results in Python, and then I can grade it from your Python model. Um, and some people really like to use Excel because they're more familiar with it, and Python is it's definitely hard to learn in the beginning for sure. Like you get through that initial learning curve, it gets easier, but people in general are just more comfortable with Excel at this point still, I think. So you might have the thought, cool, I can use either one. I'm going to just use Excel for sure. Like I'm more comfortable there. Um, but you're going to run into issues. This project is substantially more difficult doing it with purely Excel. Mainly because you're going to need to run your model 27,000 times. And that's changing 3 different inputs together. Because it's 3 inputs, that kind of throws out the data table approach, unless you're really hacking it together. And so this just becomes very difficult to do with only Excel. And so if you really are struggling with Python and you just want to do as much as possible with Excel, that's fine. I would recommend building out the base model that gets you an IRR from the given inputs, and then using Python to run the iterations side of this, because it's really probably not going to be more than like 10 lines of code in Python to do that part of it. So then you can still work mostly in Excel and use Python for something that uh, it really excels in. Though I have seen many students just go with pure Python on this project, and I think that's a good choice as well. Another thing to note about the fact that this is a random model, or at least if you're going with the internal randomness approach, which the vast majority of students will do and should do, is that I'll be providing solutions here. We'll have them down below in this document. But when you run your model, even if everything is perfectly correct, you're not going to match up exactly with the solutions because it's random. The numbers are going to be different every time you run it. So my tip there is to run the model with 1,000 iterations, check it against the solutions, and basically every number should be pretty close, nothing way off. And save your results from that, and then run the whole thing again, 1,000 iterations again, And now check your answers that time against the solutions again, and everything should be close again. And kind of all three numbers you're looking at should not be far from each other. And that will let you know that everything is working appropriately, at least with the baseline inputs. Of course, my general recommendations still apply that you only have the baseline solutions given to you, and so you need to be messing around with different inputs in your model and making sure that your model can adjust appropriately. Um, and as with all the projects that have templates, you don't want to move any of the input or output cells. And in Python, just like with the first projects, you're going to have certain variables that need to be defined to give your answers. And then the bonus for this is in two parts. First part is visualization is built into the basic problem. You need to have some visualization to get the full credit on the accuracy portion, the readability portion. But if you do an especially good job on visualization, then you're going to earn a bonus. So half of that bonus um, comes from doing a really good job on visualization. And the other half is an extension to the problem where instead of looking at 10%, 20%, 30% as the probabilities of defaults, we want to evaluate the probability of default being drawn from a normal distribution. So, what do the results look like across all the different interest rate and loan life cases, but with this randomly drawn default probability from normal distribution with a mean of 20% and a standard deviation of 5%. And then going further than that, you want to take a single input case, so single loan life, single interest rate, um, single default probability, and look at what the result looks like with different number of iterations. Try it with 10, 100,000. And you want to produce the visualizations of each, summary statistics of each. And the idea here is you want to be able to say, how precise are these estimates? When I run the model 1,000 times, how far off can I expect to be with my result? When I run it with 10, how far off can I expect to be with my result? So you want to do that by, for each number of iterations, you're going to run that in another like meta number of iterations to see across these different cases with that number of iterations, what's the distribution of the result. So the visualization part is up to 2 points bonus, and then these things together are up to 3 points bonus. And then we have template files for this as well. And you have an Excel template, a Python template, Jupyter Notebook template. Again, it's up to you whether you want to do pure Python, pure Excel, or a combination. Just whichever tools you choose to use the template for that tool. So if you have a combination model, you should be submitting both parts, which are both based off the two templates. Pure Python based off the Python template, pure Excel based off the Excel template. And just want to emphasize again, if you do the combo model, your final answer should be in the Jupyter Notebook on the Python side. And then here you can see the selected solutions. So it shows for each of the different interest rate, loan life, default probability, what is the expected IRR across a bunch of iterations, looking at the different default cases. And I went a little bit further to help you out on this because this takes, running your model a bunch of times to check it. I also gave you for the default inputs what the IRR is with the different default cases. So defaulting in year 1, 2, 3, 4, 5, and no default. Here are the IRRs that you would earn in each of those cases. So You should be checking this first, make sure you can match these numbers with the different cases in your model. And then once you have all the iteration things built out, then you can check against this solution. And the grading is the same as the first project, 60% accuracy, 20% readability, 10% formatting, 10% properly using the template, and 5% on the bonus. So that is the overview of the second project on probabilistic loan pricing. Thanks for listening, and see you next time.